So the way I explained that these lectures would go is we would start on a track that covered sort of general information, and then we would split and do two things. The first thing we would do is the study of geodesics. Geodesics and the geodesic equation. And then the second track we would study the Einstein equation. And the geodesic equation, we would do geodesics in the Schwarzschild spacetime, which I'll sort of draw like this because it's a spherically symmetric spacetime. And the Einstein equation, we would generate the metric for the Schwarzschild spacetime, right? And then we proceeded and we went down this track here and we went down this track here. We solved the geodesic equations. And then we ended up with equations that expressed, in fact, the geodesics around Schwarzschild spacetimes, and they were pretty cool, right? They were these things that sort of spiraled, and some of them kind of went like this, and all of those cool things I showed you. And we also generated the potential, right? That the potential for the equivalent potential, which you can do because of the spherical symmetry. It turned out the spherical symmetry allowed us to create these potentials for these sort of effective potentials, right? Effective potentials, which you'll discover if we ever get to it for, say, the Kerr geometry, you'll see that the effective potential analysis is really only there for the spherically symmetric case. Other cases, you have a much more complicated analysis. That's somewhat parallel, but you can't simply do a simple curve like this for anything but the spherically symmetric case, as far as I know. Of course, you could do something like that for the flat space-time, but that would be trivial. So then, but in order to understand these orbits, the solutions were elliptic functions or elliptic integrals, and they're related, so you can kind of put them in either perspective of elliptic functions. Generally, elliptic functions is the answer there. The solutions to the geodesic equations that told us our paths in space-time, given the metric of the Schwarzschild geometry, come down to elliptic functions. And then I kind of got on this tangent, which to me is sort of the point of these lectures, is to flush things out, is what are elliptic functions? And this is part of my philosophy that if you're going to do physics, you might as well take every possibility to dig as deeply as possible into the mathematics. And so that's kind of where we're at with this stuff. I'm doing these mathematical side trips, which are in some cases mathematical backwards trips, right? Instead of new math, we're kind of reviewing old math that's probably gone stagnant, that's going to get us into this area of what is elliptic functions. And we are going to finish that. We're kind of like halfway through it. But at the same time is passing, and I don't want to miss out on this track too. So I'm going to begin this track right now. And in this track, we're going to derive the metric of the Schwarzschild spacetime from first principles and from the Einstein equation. And as we do that, we will continue this later, because we really did the end part of it. This was totally demonstrated. We derived and understood the geodesic equation in great detail, and we solved it for one case, right? That mission is accomplished. Now, it's to make you comfortable with the answer is sort of what this is all about, right? What are the elliptic functions? How do they relate mathematically? I mean, to get that totally square, we have to do a bunch of complex analysis, right? Complex analysis, and that actually may be new material. So this could actually take quite a long time. I didn't quite appreciate how long it would take until I started doing it. But if you do spring for the book, Why Does It Move, for the Patreons, I do have a chapter that kind of goes into pretty good detail, but the more I study it, or the more I try to prepare these lectures, the more I realize I don't even go into enough detail in the book. As crazy as much detail as I do go into, there's a whole element of complex analysis that's not mentioned there. Anyway, I do want to finish this, but it's actually now become sort of a sidekick to the idea of studying general relativity. And many of you have actually pointed this out to me. So Very well. So now we are going to proceed down this path here and study the Einstein equations and derive the metric for the Schwarzschild spacetime, which is the very metric we assumed when we did this. Right? When we did this thing, we assumed this metric. Now we're going to derive it. Okay, so let's begin. Okay, so there she is. This is the Einstein equation. On the left side, you have the Einstein tensor, G, and on the right side, you have the stress energy tensor times 8 pi. A couple quick notes is that in our units, G equals C equals 1. Now this G, of course, is the gravitational constant. It's not related to that G. This G on this side here, that's the Einstein tensor. And of course, they're easy to distinguish. Our G is always equal to 1. Our C is always equal to 1. And if you weren't in these units, if you weren't in the GC equals 1 units, you would have, let's see, you would have a G here and I think a C to the 4th down there. So, but we are in G equals C equals 1. So we're just using the black letters for our expression. So we're going to solve this equation. What does solving it mean? Well, first, putting aside the fact that I have to explain to you what this is and I have to explain to you what that is, a solution to this equation is, and this is important, this is where people kind of go astray. They lose track of what is actually the focus of what we're doing in a sense. We're trying to solve for a space-time. We're looking for a space-time. We want a space-time, and our space-time has some specific properties. We've already said it's going to be spherically symmetric, but it's going to have a few other properties. It's going to be static, which means it's not going to be dependent on time, and we'll see what that means very specifically also. And it also is going to be vacuum. We are looking for a vacuum solution, which is a little bit bizarre to understand as well. All three of those things are important. But the actual answer for the space-time, what this thing is it is a metric. It is G, the metric, G mu nu. And G mu nu can be thought of in different ways. We've already gone through a lot of this, but the way I've been teaching it, G mu nu is a tensor, right? And it's a function that takes two vector arguments and returns a real number. And this is that tensor. G mu nu itself, the coefficient of the tensor, or the component, the tensor components, if are to be understood, and this is obviously review for those who've been following along, it is a function on the space-time. So I can put x, say, delta here. Or sometimes I would just write G mu nu of x, E mu tensor product E nu. Or I would just write G mu nu, E mu tensor product E nu, where the fact that this is a function on the space-time is implied. So this is a tensor field. A tensor field, and it is a rank 0,2 tensor field. That is what we're looking for. That is what we mean by a space-time. And this is the guy that's going to have certain properties that are spherically symmetric, static, and its derivation, how we got there through this equation, the way we set up this equation, is going to ensure that it is a vacuum solution. So the fact that it's static is going to be evident by looking at it. The fact that it is spherically symmetric is going to be evident by looking at it. The fact that it's a vacuum solution really depends on how we derived it, which is going to depend entirely on the right-hand side, which we'll talk about in a moment. So this is what we're after. And of course, we've presumed what the answer was when we studied the Schwarzschild geodesics in the Schwarzschild geometry, right? In the Schwarzschild geometry, I'll thicken my pen a little bit. You know, we talked about, you know, paths. It's like, say here was our star. We talked about orbits that could go orbit like this and cross themselves, or even more interesting orbits that come in orbit a few times and then either collapse inside or perhaps, depart after several revolutions of the center of symmetry. And we studied those and we learned how to calculate them, and we've pretty much got that in hand with the exceptions of perhaps the core level of the mathematics. But we assumed, when we did that, that we knew the metric tensor, and that's all we needed to know, because that is what defines the entire space-time as far as we're concerned. So now we want to derive this from as elementary first principles as possible. Now, when you go to a lot of textbooks, they do make a lot of assumptions, and I'm trying to do this with the minimum set of assumptions. I want everything to become evident through the math if it's possible. So my analysis, my walk through this is a layer or two more detailed than you'll normally get in an elementary general relativity course. So, of course, as usual, it may get a little bit long and pedantic, but what the heck? That's why I'm doing this, right? Is to be sort of long and pedantic. But anyway, to attack this guy, we need to understand both sides of this equation. G mu nu is the Einstein tensor, and it is equal to something called the Riemann Curvature Tensor minus 1/2 times the metric G mu nu times another times a fully contracted Riemann tensor, which is called the curvature. This is the definition of the Einstein tensor. So right now we can rewrite the Einstein equation without any trouble by writing this curvature tensor minus 1/2 G mu nu R equals 8 pi T mu nu. So now, what is it that we don't know? We know this guy. I guess I should say we know that guy, so I'll make this one green. But we still don't know, I don't think I've discussed that, and I certainly haven't discussed that, because you got to discuss this first before you can understand that. Now, strangely, I did discuss the torsion, T mu nu, right? The torsion we've actually covered. But we did not discuss the Riemann Curvature Tensor. So that's our first order of business, is to study this guy and to understand what it means. R is pretty simple to understand. R is simply the contraction of the Riemann Curvature Tensor with itself, right? So you would just raise this first index and make sure you contract it, and that's what R is. So R is very easy to understand once you understand the Riemann Curvature Tensor. So that's the next thing we have to do, is the Riemann Curvature Tensor. And we can't really advance too much without it. So we will find the time to get there, but we are actually not going to literally start this series with that. There'll be a time in the next few lectures where we will pause and we will study the Riemann Curvature Tensor in detail. My ordering of things is a little unconventional, but remember, I'm kind of presuming that everybody's been around this material before, and so maybe shuffling it around in a different order will make your brain sort of twist in a different way to see things in a slightly different set of connections, instead of trying to rebuild the same old connections from the same standard order of things. So I don't have any hesitation of jumping into solving the Einstein equation and defining the Riemann Curvature Tensor until a little bit later. And you'll see why that's actually possible. It seems like that'd be crazy, right? Because look, the Einstein equation, it's all about the Riemann Curvature Tensor, right? The whole left-hand side. I mean, how could you even begin to move? But you'll notice that there is this guy in here, and it turns out that this guy in here enforces spherical symmetry and staticness. We're going to spend some time studying the spherical symmetry, enforcing spherical symmetry onto the metric, and then ultimately you'll see that the Riemann Curvature Tensor, just like the connection, the metric connection, is ultimately defined in terms of the metric. Which means that this whole left-hand side could be written in terms of just the metric. It'd be a mess to do. I'll probably write it out at some point just for kicks. But in a sense, the left-hand side is entirely written in terms of the metric once you learn how to write this guy in terms of the metric. So ultimately, you're going to have a left-hand side that's entirely in terms of the metric equal to the right-hand side, which is in terms of this thing called the stress energy tensor, which does not have the metric in it. So you're going to have a big equation for metric components on this side and a lot of different equations, because the Einstein equation, as you notice, is not just one equation. It's one equation for every pair of indices. So you have G00 equals 8 pi T00. You have G01 equals 8 pi T01. So that's going to be, in principle, 4 times 4. It's going to be 16 different equations. And we have to pare that back as best we can. So studying the spherical symmetry is really studying how the final solution must look. Because ultimately, this guy, this last step, our answer, our space-time, must be spherically symmetric. So we can enforce that at the beginning, and that's what we'll do. And then once we've done that, then we'll diverge or we'll digress and get the details of what the Riemann curvature tensor is, and then we'll push towards the end. Okay, so now what about the right-hand side? Well, that's another thing we can put aside, because I could spend several lectures talking about the stress energy tensor, and we will, because when we study cosmology, you must know about it. There's no way to escape it. But for the star, the spherically symmetric dense star that I was talking about, or that we're going to be dealing with, or the spherically symmetric solution, we're going to be looking for a vacuum solution, which is a little bit strange, because when you think about this, we're dealing with, and I'm sure this is not unusual, but or this is not news to anybody, but we're dealing with a spherically symmetric, say, very dense star, like a neutron star. And the answer we're going to get, seeking the vacuum solution, is only valid in the vacuum. So our solution, the solution that we're creating, is valid only outside of the surface of this star. Inside the surface, this is the exterior solution. And that's a vacuum solution because it's in empty space. Inside is the interior solution. The star has, say, mass m. That solution is different. The distinction between the two is that let me go back to blue, T mu nu in the vacuum is always 0. Remember, the right-hand side, this side of the equation, tells us all about the matter-energy distribution that we're dealing with. Matter and energy on the right-hand side deforms space-time on the left-hand side, right? Matter and energy goes in on the right, space-time is curved, is on the left. All the metric of space-time is on the left, and the matter-energy is on the right. So if you're in the vacuum, you have no matter-energy, so this side is 0. That means the Einstein tensor, each component identically ends up being 0. But that does not mean that the metric is 0 everywhere. It means this expression is 0. Until you understand what this is, you don't know how to solve this. And it's going to solve that if we want it to be spherically symmetric, we have an interesting metric, a metric that's not Minkowski space. So the exterior solution, despite the fact that the exterior solution is represented by G mu nu equals 0, it's also R mu nu equals 1/2 G mu nu R, and that still gives you a unique metric. Well, I shouldn't say unique. Unique is a bit tricky idea. There's conceivably different kinds of spherically symmetric solutions. We're going to end up looking for the one that has a little bit of mass implied, that mass is all sitting in the center. You could imagine shells of matter, right, that are uniformly distributed in space or something. That would also be spherically symmetric in principle, but they're unreasonable, physically unreasonable. So even though we have now the power, because we're looking for the vacuum solution, to set this side here equal to 0. And so I can delay talking about the ins and outs of the stress energy tensor for now, because we're looking for a vacuum solution. Whatever the energy momentum tensor is, whatever the stress energy tensor is, we're going to set it to 0 because we're looking for a vacuum solution. So ultimately, this now becomes our equation in this form here, and we can now we can proceed with enforcing the other two, the spherically symmetric and the static. Now, what we're probably going to do is we're definitely going to enforce the spherically symmetric. We're going to spend a full lecture on that. The static normally is enforced quite arbitrarily and early on in most treatments. I think I'm going to let the static nature of the solution show up a little bit later when we actually solve the Einstein equation. When we actually solve it, I'm going to let that show us that the solution is static, which means we're going to carry around a lot more math a lot longer. It kind of makes this solution a little more difficult. Okay, so next time we'll begin this exact process. We'll begin by enforcing the spherically symmetric nature of the answer, and then we'll start proceeding to solve for the Schwarzschild spacetime.